Now, let's introduce a new topic that is not related to specific technique to solve exercises, but it is an interesting topic that allows us to understand how power is delivered to load. So let's suppose first to have a source, and let's represent this source with its Thevenin's equivalent. So we have a voltage generator connected in series with a resistor. And this resistor represents the inner resistance of the source side. And at the terminals of this Thevenin's equivalent, we have connected the load. Let's call the load resistance RL. The load is supplied with a voltage V and a current I. The generator supplies power to the load, but also part of the load supplied by the voltage generator is absorbed by the Thevenin's resistance as losses. What we want to know is to find out the value of the load resistance RL such that the power delivered to the load is maximized. We can investigate the behavior of the circuit before going into the analytic details by analyzing the characteristics of the two parts, the Thevenin's equivalent and the load resistance, in the VI plane. The characteristic of the Thevenin's equivalent is a straight line, like this one. The intersection with the V-axis is VTH, while the intersection with the I-axis is the short circuit current VTH over RTH. The characteristic of the load resistance is a straight line passing through the origin. Let's call this line RL prime, in the sense that if we change the value of RL, for example, we decrease the value of RL, we have another straight line with a different slope, and in this case RL double prime is lower than RL prime. So we may say that if we increase the resistance up to the value of infinity, we get the point that intersect it is the intersection between the red line and the v-axis. So this is for RL that goes to infinity, while the intersection with the I-axis is when the resistance is the smallest value available, so when RL is 0. Now let's try to analyze this behavior from the point of view of power. Now let's try to analyze the behavior of the load power with respect to the value of the load resistance. When the load resistance is 0, we are in this point here. And when we are in this point, the voltage is 0. So the power, that is VI, is 0. Similarly, when the resistance goes to infinity, the value of the power is 0 again, because in this point, the current that is flowing through the resistor, the load resistor, is 0. And so, this value, when R approaches infinity, the value of the power is 0 as well. For all other values of the resistance, the power is a positive value, and so we have a curve like this one. In other words, we can say that for a specific value of the resistance, let's call this value RL star, the power is maximum. Let's call this value P star. Now, what we want to do is to find out the analytic expression of this power. The current flowing in the circuit can be easily calculated as VTH over RTH plus RL. So the power absorbed by the load is simply RL I squared, or RL over RTH plus RL squared VTH squared. If we want to investigate when the value of the power is maximum, we have to calculate the derivative of the power with respect to the load resistance. And the formula is the well-known formula of the derivative of a ratio. So we have to square the denominator, RL to the fourth power. Then at the numerator we have to put the denominator, RTH plus RL squared, times the derivative of the numerator, that is 1, minus the numerator, RL, times the derivative of the denominator, so 2 times RTH plus RL. We can see that we have the denominator that has a term like RTH plus RL, and this term is also available in the first two terms of the numerator, so we can simplify these terms here, and we have a cube value at the denominator. So we can say that the derivative is RTH plus RL cube at the denominator, while the numerator is RTH plus RL minus 2 times RL, everything multiplied by VTH squared. So the denominator is still RTH plus RL cube. The numerator is RTH minus RL, and everything is multiplied by VTH squared. So if we want to find out the maximum of this derivative, we have to calculate the values of RL for which this term is 0. And we only have the solution that RL equals RTH. And we call this value RL star. This is the condition for maximum power transfer, that is also called load matching condition. So we have that the power delivered to the load is maximum when the resistance of the load equals the inner resistance of the Thevenin generator. Let's now calculate when the power is maximum. So when the power PL star is the power PL when RL equals RTH. If we substitute this value in the previous expression of the power, we have RTH at the numerator divided by 2 times RTH squared VTH squared, and so we have VTH squared over 4 times RTH. If we want to calculate the efficiency of this system, eta as always is the output power divided by the input power. The output power is the power delivered to the load, so it is RLI squared, while the input power is the power delivered to the load, RLI squared, plus the power that is absorbed by the Thevenin's resistance, RTH I squared. We can simplify A squared and we get RL divided by RL plus RTH as the value of the efficiency. The efficiency that we have in the maximum power conditions, let's call this efficiency eta star, is RTH divided by 2RTH. So it is 1 over 2, 0.5. So the efficiency in the condition of maximum power is not that large because it is only 50%. Okay? So the point from the engineering point of view is that we have to decide if we want to work in the condition of maximum power transfer or in the condition of maximum efficiency. In some cases, it's useful to work in the condition of maximum power, or in other cases, the efficiency plays the most important role, and so we have to increase the efficiency as much as possible. Please note that from the definition of efficiency, we have that the maximum efficiency can be found when the ratio is 1, and the ratio is 1 when RL goes to infinity. So when we actually have an open circuit at the Thevenin's equivalent terminal. A typical application of the maximum power transfer condition is studied when you have a solar panel that is supplying power to a load. So let's suppose that this is the solar panel. The solar panel produces power in DC. We have here a couple of voltage and current. Here you have the load. Usually the load is powered in AC, so you need a DC-AC converter that is also called inverter. In the middle, we have another component, and this component is something that makes it possible to see the load such that the power delivered to the load is maximum. So there are some circuits inside this block here that transforms the equivalent resistance of the load into the resistance that is required for the maximum power condition. Okay. So this device here is called MPPT, Maximum Power Point Tracker. And this MPPT, according to the different working condition of the solar panel, changes the equivalent resistance of the load such that the equivalent, Thevenin's equivalent of the solar panel has a matching load and the power delivered to the load is maximum.